Welcome to Vectors. We're going to start with this quick question. I drive 5 miles along the M1 from junction 21. I stop, and then I drive 3 more miles along the M1. For the purposes of this question, we can assume the M1 travels due north and south. Keep things simple. So the question is, where am I now? And as you've probably guessed, the answer is not quite so simple as 8 miles north of junction 21. In fact, there are a few different answers, so see if you can come up with all of them. Right, here's what you might have found. We've either got 8 miles north of junction 21, that's assuming that I drive north initially and I continue driving north afterwards, or I might only be 2 miles north if I manage to find a way of turning around and driving 3 miles back the way I came, or potentially I am now south of junction 21. But again, either 8 or 2 miles, depending on which way I go at each particular point. Now, these questions where direction matters, call for a new type of number. We can't just talk about 5 miles, we need to talk about 5 miles north. And therefore, we come up with this new sort of number, directed numbers. Now, if it's 5 miles north and 3 miles north, it's not a problem. We still end up 8 miles north. But if we're going 5 miles north and 3 miles south, that's going to give us a different result. And of course, if we go 5 miles south, followed by 3 miles north, we'll end up further south than we started. And the extreme version, where you go south both times, you end up 8 miles south. Now, the generalized version of what we've got here are called vectors. We can think about these in not just one dimension, but in 2 or 3 or even more. So a vector is defined by two key things. One is its size, which is known as the magnitude, and the other is which way it's directed. So we've got a direction and a magnitude. So we've already thought about how negative numbers give us that directional information. We've got a forwards or backwards. My children call negative numbers backwards numbers, and if they get an instruction like walk forwards -7 steps, they know to walk backwards. But movement, although it's a really powerful way of visualizing and working with vectors, is not the only way we can think about them. So I would encourage you to pause and have a think about what a PayPal balance in dollars and pounds has to do with vectors, and what a plant trying to convert sunlight into energy has to do with vectors. And what an ant farm might have to do with vectors is probably a little more obvious, but we're going to get onto each of those and look at them as different examples as we build a sense of what it means to have a vector in more than just one dimension. So let's start with the first one. Photosynthesis is what I'm getting at here, and the chemists among you will probably understand this process better than I do, but I'm hopefully not going to give you any incorrect information about what's going on here. A plant will take on carbon dioxide and water, and then using the energy from sunlight trapped by the chlorophyll, it is able to miraculously convert those two things into sugar, glucose, C6H12O6, and oxygen. This is useful for two reasons. Firstly, it makes plants delicious, so we like to eat them because they're all sugary, and it also allows us to replenish the oxygen that we're using up through respiration. This is what a glucose molecule looks like, and there's a lot going on there. As you can see from the chemical equation, there's a lot of carbon, there's a whole lot of hydrogen, and there's a fair bit of oxygen in there. And if you just get one molecule of carbon dioxide and one molecule of water, you're not going to have enough to build even a single molecule of glucose. So we do a process called balancing the chemical equation, I believe. And the idea is something like this. We want to know how much carbon dioxide, how much water we need to put together in order to produce a single molecule of C6H12O6, glucose. And of course, the byproduct oxygen, which the plant doesn't need, it will get rid of. We're also interested in how much of that is produced. And one nice way we can do this is to separate out the different elements. We're interested in making sure the same number of carbon atoms go in as come out, because that's what happens in reality. If you have carbon being used in a reaction, then it doesn't get used up, it doesn't get destroyed. We're not talking about some kind of atomic destruction of an atom. We're talking about a conversion between different molecules, different ways of combining the atoms. So whatever the number of carbon molecules is on the left-hand side, that must match the number of carbon molecules on the right. We can do the same with the hydrogen molecules and with the oxygen molecules. We can generate something that looks a bit like this. I'm using this column of numbers to represent for each molecule how many carbons, hydrogens, and oxygens it contains. And then if I multiply one of those columns by a number, it makes sense to multiply each of the values within the column by that same number. So if I had 3 carbon dioxide molecules, then that would mean I have 3 carbons, no hydrogens, and 6 oxygens altogether. Now I don't know how many I've got, so I've labeled these P, Q, and R, but we can combine them. So if we put together the P times 102 and Q times 021, and then we add them, the overall total there is going to look something like this. There's P carbon atoms, because they come only from the carbon dioxide. There's 2 Q hydrogen atoms, because you get 2 from every molecule of water. And there's 2 P plus Q oxygen atoms, because you get 2 from each molecule of carbon dioxide and 1 from every molecule of water. On the right-hand side, the same thing has been happening. So we have 6 carbons, 12 hydrogens, and 6 oxygens from the glucose molecule. We have 2 oxygens from every oxygen molecule. When we put those together, we get a different list, 6, 12, and 6 plus 2R. But because we know that both sides need to balance, we can treat each of the separate entries in our column as distinct and unrelated to the others. So the number of carbon atoms needs to match, therefore P must be 6. The number of hydrogen atoms needs to match, therefore 2Q must be 12. And the number of oxygen atoms must match, therefore 2P plus Q has to be the same as 6 plus 2R. Putting these together, we can see pretty quickly that we can calculate the value of each of those. So it turns out you need 6 carbon dioxide molecules, 6 water molecules. Put those together, you'll generate for yourself a single molecule of glucose, and you'll also get, as a byproduct, 6 molecules of oxygen. What about the PayPal example? Well, this one's a little less reliant on understanding of biochemistry. All we need here is to recognize that pounds and dollars are not easily transferable. I mean, you could convert them. It's going to cost you money if you want to convert your pounds to dollars. So PayPal and any other account that keeps track of different currencies will often have separate balances for your pounds and your dollars. Might be that you get paid in dollars from some of your clients, and sometimes you spend dollars and you'd rather keep it in dollars than convert between them. So we can think of a transaction where you have £3 and $6, and then another one, £3 and $6. Then you get another £5, then you spend $4. You can put all that together, but you don't want to combine the pounds and dollars. We're not interested in the conversion rate between them. We just want to keep the pounds separate to the dollars. Well, again, using this column notation, we can treat every single transaction, whether it involves pounds or dollars or some of each, we can treat it as a single object mathematically. 3.6 represents a transaction where you're paid £3 and $6. 5.0, you're paid £5. 0, -4, you spend $4. And again, if you want to do something twice, you can double it. It makes sense to double both of the elements within the column. This you might already recognize, and obviously, based on the name of the topic we're looking at, these we can think of as vectors. A vector being something which has a direction and magnitude. The direction doesn't make a whole lot of sense within contexts like a PayPal account or a chemical equation, but we can still visualize a direction, and it can be a really useful idea when we're using vectors to describe velocity or force. Let's take a quick example from the book here. This is from exercise 11A, question 5, and it's to emphasize one of the really important points about vectors that hopefully you remember from GCSE, but it's one of the final topics from the GCSE, so it's something you may be a little rusty on, or you might have forgotten entirely. Unlike what people say about life, with vectors, it's not the journey, but the destination that counts. It's all about where you end up, nothing to do with how you get there. It may seem a little bit strange, but if you think about the effects of, let's say, a couple of force vectors, if you push on something with a force of 100 newtons, and then there is a resistance force in the opposite direction of 90 newtons, well, we don't add those and say there's 190 newtons of force there. we take into account the direction and say the overall effect is the same as if you just had 10 newtons pushing forwards. So the net effect takes into account the direction. We do it automatically with negatives. You did it with the example when we were traveling 5 miles followed by 3 miles. The distance might be 8 miles, but your position only cares about where you end up. It's not the most efficient way to travel 2 miles north, to go 5 miles north followed by 3 miles south. And yet, as far as the vectors are concerned, it is equivalent. So that's the idea to bear in mind. If we're interested in combining vectors, we need to remember it's not the journey that counts, it's all about where you end up. So with this example, I've chosen it because it didn't even have a diagram. In the triangle PQR, PQ equals 2A, QR equals 2B. The midpoint of PR is M, find in terms of A and B, PR, PM, QM. Now the first thing you want to do is draw a diagram. This diagram is not good enough yet. There's an important thing that's been missed off. It is a triangle, it has points labeled PQR, and the precise dimensions are not important. They've not told us enough about the vectors A and B for us to know anything about the shape of this triangle at all, apart from the fact that it is a triangle. They've mentioned the midpoint of PR, so I've marked that on as M. But then they've told us that PQ equals 2A. They've used bold for the vector A. If you're writing this down, you might use an underlining rather than bold, because it's hard to do bold when you're writing things rather than typing things. But the thing that's missing from this diagram is direction. We have to make sure we know which way these vectors are going. So if we can illustrate that here, PQ is the vector 2A and QR is the vector 2B. We need to know which way those vectors are going, because whether we're going forwards or backwards along those lines makes a difference. Think about the vector A as being an instruction that if you followed it twice, it would get you from P to Q. But there's no reason it has to be an instruction you take while standing at P. You could follow that instruction from wherever you were, and it would take you the same distance, the same direction every time. Depending on where you begin, that might be something that takes you to Q, and it might be something that doesn't. Now we'll start with the first bit, PR. In order to get from P to R, you need to find a route that uses information you already have. So a route that is defined in terms of vectors that you've been told. In other words, the A and the B. So the first thing I'm going to do here is separate out PR into the two sections, PQ and QR. This is no more complicated than saying if you want to go from A to B and you have to go via some third point, then you go A to C and then C to B. So this is a fundamental idea of how vectors work. We want to travel from P to R, and we don't care about the route that we take. All we care about is that we get eventually from P to R. So if we follow the 2A instruction and then we follow the 2B instruction, then we get from P to R. Have a go at the next one, P to M, and see if you can come up with the solution for that one. And then I'll show it on the screen in a moment. Okay, so for part B, PM, we notice, is equal to half of PR. And PR is the vector we've already calculated. So that's the trick here. If M is defined as the midpoint of PR, then we know that you could get from P to M just by following half of the instruction that gets you from P to R. And since we already know the instruction that gets you from P to R, that's the vector PR that we've calculated, 2A plus 2B, we can halve it and we get PM. Now part C takes a bit more work. We're going from Q to M, and you need to choose a route that will get you from Q all the way to M. I would encourage you to pause and have a go at that for yourselves, because the journey you take might be different to the journey that I take or that someone else takes. All right, so for part C, here's my first solution. QM, I decide I'm going to go from Q to R and then from R to M. But although QR I know the value of, because that's 2B, RM is not something I've calculated. I can look back at earlier bits of the question, because that might help me, like it did with part B, referring to part A, but RM doesn't seem to appear anywhere there. However, I do have something that involves M. I've got PM. So if I can find a way of describing RM in terms of PM, then I'm sorted. Well, RM, firstly, is the same as negative of MR. So if I want to go from R to M, it's the same as following the opposite instruction of M to R. And the useful thing about MR is that it's exactly the same as PM. To go from P to M is half of the entire journey PR. And going from M to R is the other half. It's following the same instruction, the same distance, and the same direction. And I have PM already. That's A plus B, so I can put it in there, make sure it's treated as a negative. And I've got 2B, take away A plus B. Now, there's an alternative way of doing part C. You might have used this way, and I think it's slightly quicker, but the nice thing about it is that it gets you the same results. So no matter which journey you take, as long as you're careful and you're thorough, you can avoid mistakes and you can find a valid route. This one takes us a different direction. Instead of going from Q to R and then to M, so that would be Q to R to M, we could instead take a journey that takes you from Q to P to M. And for that one, you need to do the opposite of PQ. That's why instead of having QP there, I've got negative PQ. And then for PM, that happens to be a vector that we calculated in part B. So it's always worth thinking about what the earlier sections of a question have done, because you may find a more efficient route through based on what you've previously calculated. And encouragingly, it gives exactly the same results, B minus A. There's another nice way of verifying this. If we want to go from Q to M, have a quick look at what that vector would look like if you drew it on directly, QM. And then ask yourself, is it plausible that following one instruction vector B and then doing the opposite of instruction vector A would get you the same result? So we'll do a B. That means we go halfway along QR, and then we follow an instruction which is the negative of A. So that's something that takes us in the direction of QP, but only halfway. And that takes me down there. It seems to have the same effect. Combining those two little vectors seems to give the same result as we would expect. It takes us from Q to M. Now you should be able to have a go at a few questions from exercise 11A. And if you need to, there's some good examples in the book earlier in that chapter as well. Try questions 3, 4, 6, and 7, and then continue with the video. With this scenario, we're going to work through a few questions because this is more naturally what you would likely see in a textbook or an online course about vectors. We're thinking them spatially. So imagine you've got a couple of ants tunneling through the soil in an ant farm, and we're going to start with the two-dimensional case. They start their journeys from the same place. Z moves 3 centimeters left and 4 down. Bala moves 5 centimeters to the right and 8 centimeters down. The questions we might ask are, how far are each of them from their starting points? How can Z get to Bala, and how can Bala get to Z? And how far apart are Z and Bala? So for a question like this, you would begin with, if you could, a diagram. This is a lot harder in 3D than it is in 2D, or maybe do an example in 3D a little bit later. But the two-dimensional version we can represent pretty accurately with a quick sketch. And you can get a sense of how close or far away they might be. The distance we can calculate directly using Pythagoras. So we're just thinking in terms of points on a plane. And if we consider this right-angled triangle here, then we can see that the distance of Z from his starting point has got to be 5. It's a 3, 4, 5 triangle. Similarly, for Bala, we can calculate root 89. For that one, we're looking at this right-angled triangle. She's gone along 5 and down 8. And notice that it doesn't really matter whether she's gone up or down or left or right. What matters is the size of the number in this context. How can Z get to Bala? Well, in this case, we're looking for instructions that would take you from Z to Bala. You could imagine this like a straight line. So we're looking for that vector there. But often what's helpful here is to break it down into pieces, because in the same way that we described Z's motion, which we don't know the details of, we don't know if he went in a straight line or if he meandered a little bit, he ended up 3 centimeters to the left and 4 centimeters down from where he started. Well, we also don't know exactly the details of this journey, but we know that at some point you're going to have to end up 4 centimeters below where you started and 8 centimeters to the right of where you started. Now, there's a nice calculation we can do that gives us this result directly. If we start with the location we want to get to, and then we subtract our current location, It gives us an instruction for making the move. Now this is so obvious that we hardly think of it when we're dealing with two positive integers. If you want to get from 27 to 29, you do 29 take away 27. You're effectively saying how big is the number 29 relative to the number 27. How hard is it to make £1 million? Not that hard if you've already got 900,000, as it happens. It's all relative. So when we're asking how can Z get to Bala, we're saying what is Bala's position relative to Z? And in the horizontal direction, we're asking how big is 5, or how far along is 5 relative to -3. And we already know if we do 5 take away -3, that gives us the total distance between those 2 points. So horizontally, we have 5 take away -3, it's 8. And then vertically, well, -8 is a long way down, but Z is already at -4, so it makes sense that the overall displacement he needs to increase by is a smaller quantity. -8 take away -4 gives -4. So 8 to the right and 4 down. And it shouldn't be any surprise that if Bala is trying to get to Z, she has to do the exact opposite. She needs to go 8 to the left and 4 up. You can do this as its own separate subtraction, but in vectors, just like with any other numbers, A take away B is the same as B take away A with the sign changed. So instead of subtracting the vectors a different way around, you could just throw a minus sign in front. We can also choose to use either of those two vectors to answer the final question. How far apart are they? Well, we've already got ourselves another right angle triangle here. If we know the vector for how to get from one to the other, all we need to do now is a bit of Pythagoras, and we can get the distance between them. Now we're going to look at a few key results involving vectors. These will mostly be exemplified with two-dimensional examples, but they apply more generally. Firstly, as we know, vectors are defined by their size and their direction. We call their size the magnitude. And importantly, two vectors are only ever equal if their size and their direction are the same. If you've got two vectors that are the same size, there's nothing that necessarily means they have to be equal because they could be pointing in different directions. Similarly, you could have two vectors pointing the same way, but if they're different sizes, they represent different instructions. Or if they were, for instance, forces, the force might be pulling you in the same direction, but with a different strength. So if two vectors are equal, then they are equal in size and in direction. The size, incidentally, is denoted with these two vertical lines, sometimes known as the modulus function, which we could use for numbers as well. We could say the modulus of 5 is 5, and the modulus of -5 is also 5. It's a way of asking for the size of a value, sometimes known as the absolute value. By the way, you'll notice perhaps that I'm using bold type when I'm referring to a vector. If you refer to a vector in your written work, it's a good idea to underline the letter so that we know that that's what you're talking about. That's a simple trick that is generally observed. It's a convention that we find very useful because it's often unclear if you don't do that exactly when you're dealing with a scalar quantity, in other words a non-vector, or when you're dealing with a vector. Now we also have a definition of a unit vector, a vector with size 1. So imagine, for instance, that all you cared about was the size of a vector, then you could ignore the direction and just calculate the size. You could say, all right, I don't care what your velocity is, just tell me what your speed was, because that's what I'm measuring. Or it might be the opposite. It might be you care about the direction, but you don't want any information about the size of the vector. In which case, you could calculate the unit vector. It preserves information about which way the vector is pointing, but essentially you divide the vector by its magnitude, and you get a new vector pointing in the same direction as the original vector, but it has size 1. Very helpful, particularly if you're doing stuff with vectors in computer programming, because you might want to combine vectors in all sorts of different ways. You don't necessarily want the sizes to be combined. You might just want to incorporate the directions. So the unit vector is a very helpful idea. For instance, if you've got the vector 3, 4, we could scale it down by dividing by 5, which is the size of that vector, and we get the vector 3/5, 4/5, or if you prefer 0.6, 0.8. That vector is going the same way as the vector 3, 5, but it has a length of exactly 1. Now the direction can be described implicitly by writing a vector in column form, but it can also be calculated directly as an angle. So we might have the angle from north. Clockwise from north is typically how a bearing is represented. But mathematically, more commonly, we would refer to the angle as the anti-clockwise angle from the positive x direction, just like we do with trigonometry. Now, if two vectors are parallel, either they will be going the same way or the exact opposite direction. So for instance, the M1 northbound and the M1 southbound, cars on those two routes are not traveling the same way, and yet you would hope the two routes are parallel. They never cross, no matter how far you take them forwards or backwards. The subtle distinction between the definition here for vectors and the one for lines comes from the fact that a line, depending on how you look at it, either has no direction or has two equally valid directions. The line y equals x, is it going up and to the right or is it going down and to the left? It depends on your perspective. We treat vectors that are pointing along parallel lines as parallel. But we distinguish between the ones that are going the same way and the ones that are going in the exact opposite direction by saying something like, these vectors are parallel in the same sense, or these vectors are parallel in the opposite sense. Generally, hopefully you're familiar with this, the column form of a vector, we use the first element to represent how far to the right, and the second element to represent how far up. If we have negatives in there, that means we're going left or down. And if we had a third element, that third element would represent how far out or in, if you like. So if you imagine drawing a set of axes on a page flat on the desk in front of you, you probably have the x-axis going to the right, you'll have the y-axis going forwards along the desk, the z-axis will be pointing straight up out of the desk at you. We can use Pythagoras to calculate the size of a vector. So when it's written in column form, we can pull out information about the magnitude using Pythagoras. We can also pull out information about the angle using right-angle trigonometry. We just have to be a little bit careful if you've got negatives involved, because as you know, you might have an angle of 150 degrees, but your calculator is unlikely to give you that result. So make sure you draw a bit of a diagram, check that the answer you're generating makes sense. It might be you need to look beyond the principal value from the calculator. Now you can have a go at this question, see how well you've made sense of these ideas. Here is a vector written in column form. In fact, I've given you, in a sense, a family of vectors, k root 3, k. K could be any constant, so have a think carefully about what the result might be. If you're struggling, pick a value for k and try the question with a specific value. I want the magnitude, the size of the vector, and the direction of the vector. You could measure this as the angle anti-clockwise from the positive x direction. Okay, here's what I got. I got 2k for the size. If k was 1, we just have root 3, 1, and when you square both and add them together and square root, you get 2. And then 30 degrees anti-clockwise from the positive x-axis. And then I realized that I'd missed something. And a helpful idea here is to think of a diagram. There are many vectors that this could be, but they all fall into two main categories. Apart from the 0 vector, which arguably doesn't have a direction, although it does have a size, 0, all the other vectors we could generate of the form k root 3k either fit the description I gave, the size is 2 times k and the angle is 30 degrees anti-clockwise from the positive x-axis, or they fit something different. Because k is negative, the size has to be negative 2 times k. Otherwise it would give a negative answer, and size is never negative. And then for the angle as well. If we're measuring anti-clockwise from the positive x direction, then yes, we might get 30 degrees, or we might get 210 degrees. It depends on the value of k. Now this is what we were talking about when we described parallel. Root 3, 1 and 2 root 3, 2 are parallel in the same sense because one is just a stretched version of the other, both pointing in the same direction. But root 3, 1 is also parallel to minus root 3 minus 1. But in the opposite sense. So if you can multiply a vector by some number, you will be generating a parallel vector. If the number you multiply it by is a negative, then you'll be generating a parallel vector in the opposite sense. Now, we also describe vectors in a different way, we can have an ij notation or ijk if we're in 3 dimensions. We use these as names for the most fundamental unit vectors. They're known as basis vectors. They're not the only ones we could come up with, but these are a sensible starting point. If I is defined as the vector 1 along, and j is the unit vector that represents 1 up, then any other vector can be described using these. So the vector 2, 3 can be thought of as 2 lots of the vector I and 3 lots of the vector j added together. We will often refer to the 2 at the top of the vector as the I component and the 3 as the j component. And if we had a third bit, we'd call it the k component. So here in 3D, 7, 2, 9 can be thought of as 7 lots of the vector 1, 0, 0, that's I when you're in 3 dimensions, 2 lots of 0, 1, 0, which is j, and 9 lots of 0, 0, 1. So you can see how any vector could be rewritten as a single line as multiples of the unit vectors I, j, and k. Now, this is useful in certain situations. It's particularly beneficial when we're developing an algebra of vectors, which you'll get onto more in your next year when you do further maths, for instance, if you do. And it can be helpful for textbooks, for instance, to write out a vector without using complicated column notation getting in the way of the text that you're writing out. But generally speaking, I tend to work with columns more naturally than I's, J's, and K's. And there's no downside to that, really. You're not going to lose marks for writing things in column form rather than IJK. It's a more fundamental way of describing the vector anyway, so there's no requirement for you to leave things in IJK form unless a question specifically asks you to. Here's a few true or false questions for you to have a go at. I'd highly encourage you to pause and try these before you see my answers, because thinking these through will give you a much better understanding than just reading them afterwards and saying, oh yeah, I know that. If 2 vectors are equal, they are parallel. If 2 vectors are parallel, they are equal. These are different statements, so read them carefully. They're saying different things. If u equals kv, you'll notice that u and v are in bold, k is not. That means u and v are vectors, k is a scalar, some quantity. If u equals kv and the size of u equals the size of v, then u and v are equal vectors. That's what number 3 is saying. Number 4, if the size of u plus v is the same as the size of u plus the size of v, then it must be true that u equals v. And number 5, if u is a scalar multiple of v, then u plus v is a scalar multiple of v as well. So try these. I'm about to go through the answers. For the first one, this is true. If 2 vectors are equal, then they necessarily must be parallel, because if they're equal, they have the same magnitude, but they also have the same direction. And if they're going in the same direction, they are definitely parallel. Is it true to say if they're parallel, they must be equal? No. And as a counterexample, 2, 3 is parallel to 20, 30, but they're not the same size. They have to have the same size as well as the same direction in order to be equal vectors. Or the third one, v and u are scalar multiples of one another. So if k was 2, for instance, then u is twice the size of v, or v is half the size of u. So depending on which way around you look at it, each one is a scalar multiple of the other one. But here we're saying that the size of u and the size of v are the same. Now it sounds like we're saying they're going in the same direction because I've got u equals kv, and they're the same size. So it seems like this should be a true, because if they're the same size and they're going in the same direction, then they're equal, right? Well, if they were going in the same direction, then yes. But u equals kv doesn't necessarily mean they are going in the same direction. Minus 2, 3 is parallel to 2 minus 3. But because it's in the opposite sense, the 2 vectors are not equal. So you could say that under these conditions, either u is equal to v or u is equal to negative v. One of those things has to be the case. But unless you add an additional restriction, you make k have to be positive, for instance, then we can't say they're going to be equal. Number 4 will take a little more thinking. You might want to try drawing out some examples here. If you calculate the size of the sum of 2 vectors, and you get the same answer as if you calculate the size of each of them separately, does it mean that the 2 had to be the same? Well, this one actually links back nicely to the example we did at the beginning. We can think of the journey we take 5 miles north, followed by, let's say, 3 miles north. 5 add 3 is 8. The size of 8 is the same as the size of the two separate legs of the journey added together, the size of 5 and the size of 3. Whereas if the 3 had been in the opposite direction, 5 miles north and 3 miles south, then the size of u plus v, the size of 5 plus negative 3, would just be 2, whereas the size of the two separate legs of the journey added together would still be 8. So obviously we need something special to be going on with u and v, but it's not essential for u to be equal to v. We've got here that, that note is for the previous part. For this one, here's a good counterexample. U and v in this case are parallel to one another, and that means that if you were to add them and work out the total size, that's equivalent to working out the size of the two vectors and then adding them. However, they don't have to be equal, they just need to be going the same way. Geometrically, in other words, if you drew it out, what you'd be seeing is a vector followed by another vector which was pointing the same way. So as long as it's going the same way, as long as it's parallel and in the same sense, then it doesn't matter if you add up the size of the two vectors or if you add the vectors and then find the size. It'll give you the same information. But they have to be parallel in the same sense in order for that to work. For the last one, if u is a scalar multiple of v, then u plus v is also a scalar multiple of v. This one is true, and you can see it because if u is a scalar multiple of v, you can replace u with k times v, and then we've got k lots of v plus 1 lots of v. We've just got a different scalar multiple of v, k plus 1 times v. For instance, if u was equal to 3 times v, then u plus v would be 3v plus v, which is 4v. Therefore, u plus v is also parallel to v. Now you should be able to have a go at a few questions from the book. Exercise 11a, questions 8, 9, 10, and 11. And exercise 11b, questions 6, 7, 8, 9, and 10. The next bit I want to briefly talk about is geometric problems. When we're dealing with vectors, we actually have a useful toolkit at our disposal that we can take advantage of in order to do things like prove that 3 points form an isosceles triangle, or demonstrate that the 4 points you're dealing with form a rhombus, and so on. It'd be a good idea for you to pause here and write down what you know about these 8 shapes. What is it that defines them? What's the minimum required property for points to have or lines to have in order to be sure that we define this shape? If I have 4 points, what do I need in order to know that I'm dealing with a parallelogram? Okay, the next thing to think about is how would you conduct B's common tests with vectors? How would you find out if two vectors are equal in length? How would you determine if they're parallel? And how would you determine if they're both equal in length and parallel? You might think that last one is harder than the other two, but it's actually easier. And then when you've thought about those, how could you use those in concert with your definitions for the various shapes to prove the kind of results we're talking about? So firstly, if two vectors are equal in length, you could demonstrate that simply by using Pythagoras, find out the length of each one. If they're parallel, then it should be possible to write one of them as a scalar multiple of the other. So you could write the first vector and then equals k times the second vector. You then compare each element, so the two top elements, you'll have, I don't know, if you want to know if 5, 7 is parallel to 10, 15, then you put 5, 7 equals k times 10, 15. That means 5 needs to be equal to 10k and 7 needs to be equal to 15k. If when you solve those, you find a consistent value for k, so you find, oh, it turns out there is a number that all we need to do is multiply this first vector by this and we get this. And if you find there isn't a consistent value, then you know they're not parallel. If you want to check to see if they're equal and parallel, all you have to do is see if the two vectors are equal. So equal in length and parallel is equivalent to saying, are they the same vector? Or potentially is one the negative of the other one. And that's something that you would basically see from looking at the vector. So look, clearly this vector is the same as this one. I've got the vector 3, 5, 7, and this one over here is also 3, 5, 7. Or perhaps this one's 3, 5, 7, and this one's -3, -5, -7. So even if they're not equal, we can see straight away that they're the same length and the same direction, because one is the exact negative of the other, for instance. Now your definitions for these shapes, just to check that we're on the same page. An isosceles triangle is either defined as having two equal length sides or perhaps two equal angles. The sides will tie in better with what you can do with vectors at this point. Equilateral triangle, all three sides have the same length. Trapezium needs one pair of parallel sides, that's all. So if you can find a pair of parallel sides, then you've demonstrated that you're looking at a trapezium. That means that a shape like a parallelogram is automatically already a trapezium. It's just that it also has other things going for it. Just like if you see a square and someone asks you what it is, you wouldn't say it's a rectangle, and yet it does satisfy the conditions for a rectangle. From the German right angle, meaning it has right angles. Well, any square is just a special case of a rectangle. And by the same token, any rectangle is a special case of a parallelogram. It's one that just happens to have 90 degrees instead of some other angle. And a parallelogram is a special case of a trapezium. For a parallelogram, you need two pairs of parallel sides. So if you find vectors representing the sides, all you need to show is that the opposite sides are, in fact, equal vectors would be the simplest way. Because if you make a parallelogram, the parallel sides are also equal in length. Rhombus, you could do a similar thing. You would need to demonstrate for that one that the length is the same, not just for the, say, the left and right hand sides, but the top and bottom length gives the same as the left and right length. Height is a little trickier. You'd need to work with the lengths of the sides because there's nothing else easy that comes out from that. You'd have to demonstrate that it's got two pairs of equal adjacent sides. And a rectangle, you need to show that we have sides that meet at right angles. This can be a little tricky with vectors, but a good diagram will help, where you can calculate the angle that the vector makes with the positive x-axis, and that can help you to make sense of that. In fact, in 2 dimensions, you can use the gradient of the line to compare. If you've got the vector 3, 4 and the vector -4, 3, consider the gradient that each of those represents, and you'll see why that shows they must be perpendicular. And finally, the square. Two pairs of equal and parallel sides. So the vector representing the left-hand side is identical to the one representing the right-hand side, or possibly the negative of it, and the same will be true for the top and the bottom. But also, the left and right will be perpendicular to the top and the bottom. And finally, for a square, they will all be the same length. Now, a bit of a bonus section. We've talked a bit about 3D. We're going to look in a bit more detail at this. I'm interested in the length of the vector OB. In other words, from the origin to the point B that you see up there. And it turns out Pythagoras works really well, even in 3 dimensions. So I want to get from the point 0, 0, 0 to the point 3, 4, 12. You can see we've moved along the red x-axis 3 places, we've moved along the green y-axis 4 places, and then up the blue z-axis 12 places. So if you imagine that squared grid as being squared paper sitting on a desk, then you can think of that red axis as heading to the right, the green axis forwards in front of you, and then the blue axis straight up out of the desk. And I would like to know the length of that vector. But it's a line in 3D space, and Pythagoras only tells us about 2-dimensional triangles. Luckily, though, we can construct a relevant triangle. And in fact, that's exactly what I've done here. If this is the point B, we can get the foot of the perpendicular down here at the point A. So we move along 3 in the x direction, 4 in the y direction, and then just stop there. We've not moved anything in the z direction. That point is on the xy plane. The point 3, 4, 12 is directly above it. So we have a right angle between OA and AB. That is the right angle triangle we can use. We have a bit of work to do first, though. A relative to O, we've got the vector, but we don't have the length. Well, again, we can do a bit of normal Pythagoras here. The point A has coordinates 3, 4, 0. So we can ignore the z coordinate and focus on the x and y coordinates, and hopefully you can see why OA has a length of 5. We could build it into a 3, 4, 5 triangle, if you like. Now, the distance from A to B is 12 because it's vertically up 12 places. And then finally, we could apply Pythagoras to this triangle, which is right-angled, and the side we care about is the hypotenuse. Or you might notice this one's another Pythagorean triple. It's a 5, 12, 13 triangle. So writing it out as a formula looks a bit like this. To work out the length of OA, we need to do 3 squared add 4 squared and then square root it. So we get this bit here. But then if we square that, because that's one of the shorter sides of the other right angle triangle, it's as if we'd never bothered square rooting in the first place. We just get this bit. So if you look at it, turns out it doesn't matter which way we approach this, we're just squaring all 3 coordinates, adding them together and square rooting. More generally, you can apply the same technique to any 2 points. This is the completely generalized formula. All you need to do is identify the difference between the x coordinates, the difference between the y coordinates, and then tack on the difference between the z coordinates, square all of those, add them together, square root, and that gives you your total distance in 3 dimensions. This is known as the Euclidean distance because Euclid did a whole lot of work with geometry, and it's effectively what we would treat as the natural way of measuring the distance between 2 points. In 1 dimension, it works trivially. The square root of something squared is the thing itself. In 2 dimensions, we know it as Pythagoras' theorem. In 3 dimensions or even more, it still works. Now, not everything is measured using this form of measurement for distance. For instance, if you're trying to get from one building to another in the middle of New York, you can't travel like Spider-Man. You're going to need to follow streets and avenues and go 3 blocks east and 4 blocks north. And we have the city block metric, which is a different way of measuring distance. And A would be a distance of 7 away from the origin if we followed that. You could do some of your travel horizontally and some travel vertically bit by bit. So you could move, say, 1 in the x direction, then 2 in the y direction, then another 2 in the x direction, then your final 2 in the y direction. But ultimately, you'll still end up traveling 3 in one of those directions and 4 in the other one. But in terms of the actual as the crow flies distance, the straight line distance, Pythagoras works, and it works in any number of dimensions. One nice way of thinking of this would be if you've got data that maybe is not spatial data at all, but you've got information about how an athlete performed in say a pentathlete who's done 5 different events, and you've got another pentathlete who's done 5 different events. Now, they might have done better in some events than the other person and worse in some than the other person. But it might well be that you can see how close, in some sense, how close the 2 athletes are in terms of their skill sets by finding the Euclidean distance between them. That means that if they're particularly close with one specific skill or competency, then that's going to show up as a small difference between the numbers. And if you add together the squares of all the distances between the various numbers and square root it, you get a pretty good measure of how close they are. Amazon does a similar thing when it's checking to see if you're likely to want to buy a particular product. It does something called clustering. You might have a many dimensional space where effectively your likelihood of buying a product is calculated based on how similar your preferences are to a bunch of other people. And there will be clusters of people who have similar preferences along different axes, how likely they are to buy decaf coffee, how likely they are to buy reusable toothpaste or whatever it might be. And then you figure out what those people like, basically not by thinking about it, but just by looking at it on a multi-dimensional graph and seeing who's close to them. And then you just suggest things that those people also bought. We're going to come back to the ants problem finally at the end with vectors in 3 dimensions. Remember now we've got this 3D Pythagoras thing that we can make use of. So you can have a go at proving this in general. We did it for a special case, the 3, 4, 12 point, but you can try it more generally with A, B, and C if you like to get it cemented in your head. We're also going to try this question. So now we have a very similar norm to what we had before, but the numbers have changed a little bit. We've now got 3 dimensions instead of 2. So Z is moving 2 centimeters to the west and 5 centimeters down. Bala moves 10 centimeters east, 4 centimeters north, and 2 centimeters down. And we've got the same sorts of questions we want to ask. I'd recommend you pause and have a think about this, see if you can make some headway on it before I go through it. Here are these points represented in 3 dimensions. And one of the main reasons I put this in is basically to demonstrate how hard it is to represent 3-dimensional vectors at all, even if you're allowed to use some kind of animation. It's so difficult that I wouldn't recommend you attempt to draw accurate diagrams, because your diagrams will, even at best, be an incomplete representation of the truth. Instead, you want to build a good enough intuition for what happens that you can draw a wildly inaccurate diagram, but at least represent on it what is true enough for you to solve your problem. Think of it a bit like the London Underground map. Now, that map doesn't show you how far away places are from each other, and it doesn't show you which direction you will need to go from one place to get to another. But what it does show you quite effectively is the connections between them. It shows you the information you need. So although you look at the map and you know it's not realistic, you can still use it. That's the same sort of thing you'd want to do with your diagram. Now here, I've got a diagram that I'm going to use, but I'm going to take it with a pinch of salt, because I can't necessarily assume that what I'm looking at is exactly what's happening. Depending on the perspective I look from, I might be seeing different things. Now, if you recall, we can use vectors to represent all kinds of things. We used it to represent the number of carbon atoms, hydrogen atoms, and oxygen atoms in a chemical equation. We used it to represent the amount of pounds sterling and the amount of US dollars that you had in a PayPal account. We can also use it to represent how far east, north, and up you might be. And we might represent that with X, Y, and Z coordinates. Just like originally, when René Descartes gave us the Cartesian coordinate system, he was lying in bed staring at a fly buzzing around his room. And the idea of measuring the distance from one wall, the distance from another wall, and the distance from the floor popped into his head, and that was the Cartesian coordinate system that we now know and love. So interestingly, it was 3-dimensional before it became 2-dimensional. This XYZ approach is why we use X and Y, I suppose, instead of Y and Z as the last 2 letters of the alphabet. They are the last 3 letters of the alphabet, and perhaps we don't always need Z because we can focus on a 2-dimensional simplified version for certain problems. So how far away is Z from his starting point? This is actually effectively a 2-dimensional problem because he hasn't moved north at all. You could describe his coordinates in 3D using a 0 for one of them. -2, 0, -5. And Bala is going to have a 10, 4, -2. We can use Pythagoras for Z. We can use Pythagoras for Bala. How can Z get to Bala? We use the same sort of process we talked about before. We can subtract his current position from her position, and that will tell us how we can get from one place to the other. You could think of this as a journey, just like we did near the beginning. If Z wants to get to Bala, one way to do it using known vectors is to go back to the origin and then forward along here. So he needs to do the opposite of his vector and then her vector, basically. Z is going to do the opposite of -2, 0, -5, followed by the normal version of Bala's 10, 4, -2. Now, if you add them together, you find that the vector comes out cancelling out in some cases. So the -2 and the -5 mean that he only needs to travel 3 in that direction because he was already some distance down. She was a little further down, so he's got a little way up to go. In terms of the 10 and the -2, because they've gone in opposite directions when it comes to east and west, he's got further to go than if he just stayed put. And in terms of the north, he hasn't gone any distance north, so the same distance as he needs to. If you find it helpful, you can just think in terms of one number at a time. How do we change -2 into 10? You add 12. How do we change 0 into 4? You add 4. How do you change -5 into -2? You add 3. That's where the 12, 4, 3 comes from. Bala can get to Z using exactly the same vector, but with a minus in front. So it does the opposite thing. How far apart? All we need to do for that is 3D Pythagoras again. We can use the vector that goes from Z to Bala, square all of those terms, and add them, square root, and there's our answer, 13 centimeters.